Hey guys, it's Mr. Sheeline here for the Unit 8.2 notes, looking over electricity and currents. Okay, so we just got done with static electricity. We were looking at the idea that static electricity is the buildup of particular charges within a system, and those charges really not going anywhere. So now with electricity and currents, this is where, okay, well, you can build up charges maybe statically or maybe just from a particular source, and we can move them throughout what's called a circuit. We can make a current of electricity and use that current to power things like lights, like appliances, cars, anything that you can think of that, and pretty much most things you use every day. So, all right. So getting straight to it, just remember, as a quick little reminder, hey, remember, electricity is able to move because of atomic particles, so specifically electrons, and also where protons are at, and just the sheer fact that protons exist, for the most part, allow electrons to be placed where they're at due to those electromagnetic forces between the protons and the electrons. So just remember, everything in the world, everything in the universe, as far as we can tell, is made up of atoms. And it's that we really are going to be looking at those electrons mainly, that are going to be moving from atom to atom, is that's electricity. Okay, now we have to understand the charges of these things, and we also have to, and this is kind of a weird transition, I'll say. Like this right here, this material is a weird transition, from static to current electricity. So we have to know the charges of these guys, because we have, in order to understand how they move within a field, we also need to, and how they affect the field, we also need to understand their charges. And then from the charges, we then have to understand Coulomb's law, because Coulomb's law is going to more or less have us better understand how more or less energy is, this electrical energy is created. So here's what you need to notice. So what you need to notice is the fact that the electrons and the protons have roughly about the same charge. One of them happens to be positive, one of them happens to be negative. So electrons have a negative 1.60 times 10 to the negative 19th coulombs. And then protons here have a positive 1.6 times 10 to the negative 19th coulombs. Okay. And you're probably wondering, well, what the heck is this coulombs? What is this coulombs? What's the word? Units. Roughly, we won't get terribly into this. Really, we won't get into it all. Just understand that we measure the amount of charge. The amount of energy in coulombs. Okay. So, and that's what Q stands for, if you didn't know that. So Q in physics and chemistry is always used as the symbol for heat energy. For in this case, it's going to be electrical energy. So Q is just energy. So Q, in this sense, is electrical energy. For electrons, that charge is negative 1.6 times 10 to the negative 19th coulombs. Again, and it's the same thing for protons, just positive. And what we're going to do is we can then manipulate a particular, or at least not manipulate, I shouldn't say that. We are able to set up something that should look quite familiar. So we can measure the amount of force in a field using these charges like so. So if we were to think about this, remember we worked with fields and field lines. Okay, well, how can we measure the forces in a field? How can we measure the forces in a field when we have particular particles in there? So a question that would be here, using Coulomb's law, if we were to put two protons roughly about a millimeter apart from one another, or 0.001 meters apart, what would happen? What kind of force would we see between them, right? Because we know that these two guys, when we were looking at when we were drawing their field lines, this is what we would see. We would see something that looks like this, right? We would see a whole bunch of repulsion. We'd see a whole bunch of lines like this, right? Because the energy from a positive particle is going to push away from itself. That's how we see it when it's in a field. So we know that they're going to repel off of one another. And if they're repelling off of one another, that must mean that there's some sort of force between them. And we can measure that force with their charges using specifically this equation right here. And that equation right there is Coulomb's law. And we can actually answer this question pretty quickly, okay, and actually quite easily. Oh, no, don't do that. Now, but let's break down this equation real quick. So we have Q is equaling to, again, the charges. We have D, and I'll also add this. It's D or R. So there's going to be an iteration with D, but there's also an iteration with R. So it's either R or D. Is the distance from center to center. K is going to be Coulomb's constant, and Coulomb's constant is basically just it's almost similar to the universe. It's almost like big G. It's Coulomb's constant is the idea that no matter where you're at, there's a constant force, measurable amount of force due to the charge of per the amount of charge of a particular product, any distance you're away from it. Okay, so Coulomb's constant is K, and it's 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. Okay. So, excuse me. And so again, what Coulomb's law is concerned with is measuring the amount of force that would be felt between charged particles within a field. So, and we have to understand, and the reason why we're doing this, we have to understand how these particles interact with one another, so we have a better understanding of how then we can measure how much energy is coming out of a system. So F is attractive if the charges are opposite. F is repulsive if the charges are like. Now, F is going to always be positive. We're always going to make it positive because we're actually going to say it's the absolute unit of between these two. The product between Q1 and Q2, when we multiply them, is always going to be positive. We're using the absolute values here. We just then at the end, when we calculate the force, have to remember, oh, that's right. We had two positive things. We had two positives because it was two positives that we know that they're going to repel one another, and we know that they're going to repel one another. And excuse me. And we have to just make note of that in our answer. Okay. Now I mentioned though that this equation should look very familiar. Okay. And the familiar, oh my God, it should look quite familiar to you. And what it's super duper similar to is Newton's law of universal gravitation. Remember, Newton's law of universal gravitation here is simply just F of G is equal to big G times the mass of one object times the mass of the other object divided by the radius squared. And the radius is the distance from the center of one object to the center of the other object. Oh, excuse me. Sorry. Electrical force here is roughly about the same thing. It's just we are measuring two different forces. So universal law of gravitation obviously is measuring the amount of gravitational force felt between two objects due to their masses. Coulomb's law here is measuring the amount of electrical force that is felt between two objects due to their charges. So it's a difference between the change in space due to mass, a change in space due to a particular charge, how energy flows between them. So it's roughly, we use kind of the same setup, but we are using two very different variables. We're using charge for Coulomb's law. We're using mass for gravitational force. But big G and K are have like the same kind of difference here. They're very similar in their setup. Big G being just the universal constant of gravity basically never leaving you. K is the more or less universal constant that charges never leave you within a field. Okay, it's roughly, or at least we can boil it down to those very, very simple ideas. So they're very, very similar, and we're going to give this a go and try to figure out. How to calculate this. So But thinking about it now, because I'm doing this on my Chromebook, I'll actually have a separate video walking you through how to calculate these. So, but do try to answer these questions first on your own. What is the electrical force between two protons when they're a millimeter apart? What's the gravitational force between two protons when they're a millimeter apart? So go ahead, give that a go yourself. Again, I will. I'll have a separate video walking you through because I just don't have enough space on here to do this. So go ahead, try it out on your own. Go to the other video that will include that material, me solving these problems in a bit here. Okay, but to kind of keep moving on, I will answer at least no, because I'll answer that in the other video. So I'm going to skip over that. Okay, so the idea is that we went through all of Coulomb's law to understand how charged particles interact with one another in space. Okay, we understand the field lines, or we should understand the field lines, and understand that those are actual forces, electromagnetic forces within electrical forces. Electrical forces that are of charged particles within space. Okay, well, what if we have a whole bunch of these particles moving around? What can we do with that? So this is where then we transition into more or less just electricity that we think of every day. So what is electricity, or at least current electricity? Well, it's a steady flow of electricity through an electric current. Okay, so the question has to be, well, what's a current? So a type of electricity is in our homes is current electricity, and what's current electricity? It's a steady flow of electricity, and it's moving through what's called a circuit. And a circuit is, as it sounds, circuit means to go around. A circuit, you could also think of, if you've ever heard it in racing terms, a circuit is more or less, as far as I understand it, it's like a single lap. It's the map of the track that the guys are on, and you do a single circuit, you go around once. And so it's kind of the same thing here. A circuit is just it's a circular path, semicircular path for electricity to run through a system, specifically through conductors. Okay, and this allows the energy to flow from power source to an appliance, or just from one end of the power source back to the other, but that can be silly and in some cases quite dangerous. And you don't really want to do that. And we'll sort of kind of get into that, but not in terrible detail. Now, I mentioned the word current. So the flow of electricity around a circuit, it's an actual measurement, and we call it the current, and we can measure how much it is. And we measure a current in amps. Okay, the amperage of a current. It's basically how quickly we're allowing. It's how quickly we're allowing these bundles of energy to move within our system, and we measure them again in amps. Okay, and again, it's the amount of electrons passing a given point in 1 second, or the amount of charge that flows through a current or a circuit. So to understand the difference between a current and what voltage is, okay, because they're not the same thing. Voltage is like this is the bundle. It's a measurement of how much energy we put in a bundle. Oh my goodness. It's how much energy we put in a bundle. I can't write all that out, so I'll just say it. So again, voltage is the amount of energy per bundle, roughly speaking. Amps is how many of those bundles that we're going to shoot out. Like, how quickly are we going to shoot out those bundles? That's what amps are. So that's why for electricians, they have to be super careful how many amps a number of products will have, or appliances will have in a house. Because if you have too many things pulling too many amps, you can trigger the system, and if you have an old house with fuses, you're going to break fuses. If you have a more contemporary house with a breaker box, you're going to have to be flipping switches all the time, and you're going to have the city, whatever city you live in, giving you a whole bunch of hassle because they're like, hey, what's the big deal here? Like, we're seeing a lot of surges at your house. That's not good. Because again, there's only so many amps you can toss throughout a house. Okay, so just as an example, I guess, a verbal example of where it's applied, why we care about amps. And actually, if you take a look at any electric appliance, there should be a place that should tell you input output of how many volts and how many amps that they're going to be taken out, and then how many amps and how many volts that it can take, like that it can transfer. So it's an interesting little, or it's a neat little thing. So go around if you ever get the chance in a bit here. Go find like your little outlet box, not outlet box. What am I thinking of? Your little plug box for your phone. It's basically just a little transformer. It's an adapter that changes it from an AC to a DC, and it also kind of shrinks down the amount of voltage from 120 volts, running at however many amps your house is running. It shrinks it down from 120 volts down to usually like, usually it's like 5 volts per 1.5 amps or 5 volts and 2 amps. So there are some that are the superchargers where they'll shrink it down to 9 volts sorry, not 9 volts, but it'll shrink it down to like 5 volts at 3 amps, which is actually 2.7. Anyway, I'm getting you lost here, so let's just keep on going. So again, that's current, and the symbol we use for current, by the way, is a capital I. So again, 1 amp is the amount of electrons passing through a point in 1 second. So we can so to understand that, because again, it's the number of electrons, well, 1 amp is going to equal to 1 Coulomb. 1 Coulomb has this number of electrons. It has 6.25 times 10 to the 18th power electrons. So all this is right here is just the flip side. It's just the flipped version of the charges in the electrons. So remember, the charges in electrons, there's a negative 1.60 times 10 to the negative, 19th power. I think off the top of my head, 19th power coulombs. So here's the switch. If we have 1 Coulomb, how many electrons does it take to have 1 Coulomb? 1 Coulomb is equal to 1 amp. Okay. So therefore, if the current flowing through the wire or toaster in a hairdryer is just a single amp, that means that there's roughly about 6.25 times 10 to the 18th power electrons flowing past that every single point, every single second. Okay. So that then will bring us to some practice. So let's say you have 2 amps. Let's say you have 12.6 amps. Let's say you have this number of electrons passing by those points at every second. Okay, give these a try. Convert these, because this is pretty much just dimensional analysis. Convert these. If you're given the number of amps, well, how many electrons are you passing through? If you're given the number of electrons here, how many amps are you running through? So go ahead, solve these. I'm not going to solve them on here. I'll do that in a separate video and then check your understandings. So go ahead, give these a go, and then watch the check your understandings video after you're done here, or at the same time. It's up to you. Whatever. So Ohm's law. Okay, so we understand Coulomb's law. Coulomb's law is again the interaction between charges within a field and measuring the amount of force felt between two particularly charged or specific charged objects. We then went into what current electricity is, what amperage is, what symbols we use for amperage, how we can know the number of electrons moving through a circuit using those conversions. And now we're coming to Ohm's law. So Ohm's law is kind of concerned about what affects a current. So in Ohm's law, we have the current equaling voltage divided by resistance. Now, I briefly mentioned that voltage is more or less just the amount of, or the amount of energy per bundle that you could say. That's what voltage is. It's how much energy do you have per charge? How much energy do you have per little bundle of energy? Okay, that's what voltage is. Resistance we really haven't talked about, and I believe I've got a little thing about resistance. Oops, wrong way. Got a little thing about resistance on the next slide here. So Ohm's law is to say this, that the current is going to be equal to proportionally equal to the voltage, and then inversely direct proportionate to the resistance. And just listening to that word resistance should tell you what it does. We'll get to that in a second, but it's to say this. Again, it's to say this, that current, how much or how quickly we're shooting energy out is going to depend upon how many volts we have, and it's going to depend upon how much resistance there is. Okay, so what I have here, and hopefully it's still showing, or it's taking me to this FET simulator. Yeah, it looks like it should be taking me to this FET simulator. Hopefully this will load up. So just to quickly show you, and this is a clickable link. So if you go to the Google Slide version of these notes, you just click on this and it'll take you to this, or you could Google it. And it's just a quick show you that, oops, and I forgot that's the thing. So I'll turn down the volume. So as you can see, I here in the equation is our current. Here's also our current. Okay, here it's measured in milliamps. Over here, this image is going to tell us the change in our voltage using batteries, and also showing the number of voltage right here, and also right here. This little guy right here is our resistor. And if you notice that when we decrease resistance, we lose those little dots, but as we increase resistance, we're increasing the number of dots in there. Okay. But here, if I restart this, here it is, where we've got roughly the same number of we've got equal parts voltage, equal parts, roughly speaking, or at least in order to have our current at 9 milliamps. Okay. When we increase voltage and we keep resistance the same, Ohm's law states that the current should increase, because remember, current is proportional to the voltage. Okay. And then as we decrease voltage, we decrease our current. Okay, well, let's put voltage back to where it was. Now, if we increase resistance, we're decreasing the current. But then if we decrease the current, we're going to increase the current. Okay. This is just simply Ohm's law. It's just to say that again, you increase voltage, you increase the current. You increase resistance, you decrease the current. Okay. But resistance and voltage are not related, or at least they're not directly related to one another. Because if you notice here, if I change the voltage, nothing happens to the resistance. Okay, the resistance stays the same. And the same thing goes, if I change the resistance, nothing happens to the voltage. And the question is why? Why does resistance not change the voltage? Why does voltage not change why does voltage not change the resistance? Well, understand, look, voltage is in the batteries, resistance is in this little resistor right here. So they're two physically completely different things. They for the most part, don't affect one another. They only affect how well things move throughout a system. Okay, so that's Ohm's law in a nutshell. Okay, that's Ohm's law in a nutshell. Okay, so then your question has to be, all right, well, I kind of know what voltage is. Well, what's resistance? So resistance is it's a physical component that you put into a circuit that resists the flow of a current. Okay, so it's going to and it's not something you just accidentally put in. It is a natural thing that you can measure within particular materials. Certain metals have a different, just naturally due to their atomic structure, have different resistance. That's why we don't put iron in our electrical boxes. We don't use iron or at least pure iron. We don't use pure iron to connect wires to, or we don't use iron wire to connect our lights and to light our lights. Okay. And that's why we use copper, because copper just happens to be a much better conductor. And it's the opposite of it's not a resistor. Okay. But sorry, got lost there. But a resistor is purposefully is a little component that's purposefully made to change the current. Because sometimes, especially like in your house, you don't exactly want like, let's say if you have an 80 amp house, you don't want to have 80 amps pumping out into, say, your laptop, because you will literally catch your laptop on fire. At least you'll break the battery. Actually, in this case, you just break the battery and then you'd have a broken laptop. And so what you want is some sort of resistor or transformer that will kind of shrink down the current going to a particular appliance so that you don't break it, or you don't, at least over time, damage it. So this is why, as an example, when you're talking on the cell phone a lot, or if you're trying to, if you talk on the cell phone a lot, this is why your cell phone gets hot. Is because there's a bunch of energy moving from your battery to the microphone to the speakers to a bunch of other components within the phone all at the same time, and all that power has to go through a number of resistors, and those resistors are going to change the electrical energy into thermal energy. Because again, if you have too much energy moving from the battery to whatever small little product you have, a little appliance you have in your phone, you may break that appliance. You may break your microphone. You might break your speaker. Okay. Now, and this is why you're not supposed to. This is why you're not supposed to really charge your phone and do 5 different things at once, because there's only so much there's only so much your resistors can do. And if you've got 5 things, if you're doing 5 things all at once and you're charging your phone, okay, there are resistors that go to your battery, and so you're just increasing the temperature of your phone. There's only so much temperature it can reach until it either breaks or and I know for my phone, it will actually shut itself off when it reaches a particular temperature, which is a really nice feature. So it's just something to keep in mind. But we use resistors to increase or decrease the flow of a current depending upon the amount of volts in the current. Conductors have different magnitudes of resistance, and I mentioned that already. This is again why we don't use iron, we use copper, because there's just a difference in the natural resistance found in particular metals. And so here's Ohm's law, or why we want to really understand Ohm's law and take advantage of it, is because having resistors in particular appliances can not only just save our appliances, it can also potentially save our lives. Okay, because again, you don't want 80 amps going from a wall socket to your laptop over a long period of time, because it may catch fire. It may cause a lot of damage to your appliances. It can just be bad business. It also can be quite potentially dangerous if you have exposed wires. Okay. So I'm not going to show this video. You guys can go ahead and watch this video on your own, but it's going to start playing here. So let's just skip that. No pause, skip it. So again, you can watch this if you pull up the Google Slide version of these notes. You can go ahead and watch them on your own. Watch that video on your own. Okay, so now we're getting somewhat towards the end of all of this, and that's basically mapping out circuits and mapping out how energy flows throughout a system. So current electricity is the flow of electrons through a circuit. We know this, and we saw that in just this previous picture here. So here, these are very specific drawings, and so we have here the circuit here. And energy, I think, and I kind of skipped over this, energy is going to flow from negative to positive here throughout this circuit. And here we have the switch. Okay, here we have the light. Here we have the battery source. We have the, and this, we're going to learn how to draw these kind of circuits. Okay, so here are examples of how we write these out, how we sketch these out on paper. And then here's what they look like in some circumstances in life. So here's copper wire. So connecting wire is just straight line. That's a symbol. Here's a circuit component. So it can look like this. And here we'll use this to connect, to whatever power source or wherever it needs to go. This is how we draw a switch. Now the location of the bar here, typically you want the way you draw these, and you'll see these. You'll see this going forward. You want the flow of energy should, when you draw these, the energy should be moving towards this closed end here and not the open end. Typically, I'm not going to be too bothered by that. If you flip it, just to let you know, as long as you show a switch in this form where you've got this line and then it breaks and these 2 little dots, okay, I'm fine with that. But here's what the switch may look like in real life, or it can look like a light switch. Okay, here's the resistor or the load. Okay, so, and I forgot there are examples over here of what these would be. So resistor or load, here's what a resistor looks like. super duper simple looking little resistor, and these little bars do mean a very specific amount of resistance. There's a very specific amount of ohms that will be put into the circuit. We won't get into that. I'm not going to expect you guys to remember and be able to read any of that. Just you should know what a resistor looks like, but not be able to identify. I don't expect you guys to identify how many ohms of resistance there's going to be in a particular resistor. And then your power source. So this is how we draw a power source. Okay. And this one happens to be multi-celled, and that's why it's got big line, little line, big line, little line. And then you move it out to your connecting wires. And then here's, of course, we all know what a battery looks like. And then here's a cell. Okay. So here it's a single whatchamadoozits. This is how we draw like a single component here. As an example, a battery. Here's how we draw a light bulb. Of course, here's our light bulb. A voltmeter, an ammeter. So volts. A voltmeter measures how many volts. An ammeter measures how many amps. Okay. Now when we do this, we're actually going to use what's called a multimeter, which can measure amps, and it can also measure volts, and it can also measure resistance. That's why it's multimeter. It can also measure temperature as well. But it's basically the same thing. It's a circle with an M in it. It's no big deal. But we're gonna practice. We're gonna be practicing how to draw these in the next few days, and kind of put together some circuits, which would be pretty cool. So the cell stores chemical energy. Obviously, that's what batteries do, and they transfer that chemical energy in the form of electrical energy in a circuit. So when two or more cells are connected together, this is when we call it a battery. So that's what a battery is. So if I go back to the image of that battery, if you notice real quick, you see these lines right here. Those lines are actually that's a physical separation between different cells. So you can a battery is a single like double A battery is a cell. When you put them together in a series, then it becomes a battery, just like this, okay, or at least like a flashlight, okay. When you put it together in the form of like say a flashlight. Okay, so but there are individual cells in here, and they're all interconnected, and they all pop out with the negative over here, and then the positive nodes over here. And it is a specific categorization. The cell's chemical energy is used for pushing a current around a circuit. Okay. So a circuit can be described as either opened or closed. So a closed circuit means you've got a running circuit. If you've got everything connected to one another, it's a closed circuit. You should have power moving from start to finish. Okay, so the circuit operating and the current is flowing, the light switch is on. So that means that because you have that flow of energy, the light should be on. An open circuit is when you turn things off. So you've now opened up the circuit, just like this GIF is showing. And now what you've done is that you've opened up the circuit, and now you are showing that the flow of energy has been interrupted. You've turned off whatever appliance that you're using. It's as simple as that. Okay. An electric current is a flow from microscopic particles called electrons flowing through wires. We already know this. So in what direction is it going to flow? Remember, currents flow from negative terminal to positive terminal. So to kind of draw this, to finish this drawing, I should say, there's little itty bitty yellow dots on here. And actually, I'm going to make them orange to make them stand out a little bit more. Okay, so it's going to be moving in this direction. This is the direction that these are going to be moving throughout this circuit. So it's going to be moving, again, from negative to positive. Okay, this is the direction that it's moving. And that's how we have to draw this. So notice, again, big line here, positive. Little line here, negative. And then so you're going to go, and you can almost think of it like it's beginning to draw an arrow. Okay, you can almost think of it like that. Okay, this is the direction. This is how we indicate the direction of the current. Okay, it's not just because we, for funsies, wanted to show, oh, this guy's little, this guy's big. No, it's to indicate the flow of the current in a what could you say? It's to indicate the direction of the current in a or the direction of the current in a very specific way. Okay. And so we're going to be practicing two kinds of circuits, two very simple kinds of circuits. There's one that's called a series and then one that's called parallel. Okay. So a series circuit is going to basically just have everything on a single line. They're super duper simple and like crazy simple. And all it is you have the flow of energy. You have the flow of energy like so, just moving from one object to the next in a series. Then you have parallel, okay, where you're going to have the energy moving through and they're going to equally separate to both components here and move down, okay? So as an example of a series circuit is what a lot of really cheap Christmas lights are on. These series circuits, so that this means that if you were to lose a light, all the lights on the Christmas tree are gone. That's a series circuit because what you've now done is you've opened up the circuit. Electricity is not moving through the rest of the circuit, so you do not have a what's it called? You don't have a current anymore. Parallel circuits are the newer, bit more expensive Christmas lights where if this guy goes out, that's A-okay. This guy can still run. Okay, and it's much easier to know what lights to fix on Christmas lights. So think of it like that. So if you ever have a Christmas tree and you've ever had to figure out like, okay, which bulb is dead, that's on a series circuit. If you've ever been like, oh, that guy popped out, but this guy's still running, so I can just replace this guy, well, that's on a parallel circuit. And it's arranged this way where the energy is going to flow as long as the switch is closed. It's going to flow equally through both parallel paths here, and it's going to move throughout the circuit all nice and easy. Okay, so the components are connected to end, one after the other. They make a simple loop. If one bulb blows out, this is for a series circuit, all the bulbs blow out. But again, for a parallel circuit, components are connected side by side. The current has a choice of routes. If one bulb goes out, there's still a complete circuit, so the other bulb will stay alight. Okay, and so there's some real life images. So here is what a series will look like. Here's what parallel will look like. Okay. And we're going to practice putting these guys together, and we're going to practice putting these guys together and practice drawing these out. So that's all I have for the notes, guys. Make sure you go watch the Check Your Understandings as well. And I'm also going to include a bit about also that Coulomb's law walkthrough on that as well. So if you didn't check those out already, make sure you go back and do those. That's the end of the notes. So